Okay. All right. So Thursday we talked about the natural log function, and we defined the natural log of x using calculus, using an integral. It was defined as this area as you go function, and if you go through, you can use properties of the integral to prove that this is essentially what the graph looks like. Okay. Now, one thing you may notice about the graph, which we once again proved using properties of calculus, is that the function is always increasing. That means it's going to be 1-to-1, passes the horizontal line test, so it has an inverse. And so we know from pre-calculus what that inverse is going to look like. We can just reflect the graph across the line y equals x. The vertical asymptote x equals 0 is going to become a horizontal asymptote y equals 0. The x-intercept 1, 0 becomes a y-intercept 0, 1. And the point 1, e comma 1 is going to go to the point 1 comma e. And we're still going to be increasing. The slopes will still be positive, but they'll be the reciprocals. And so it'll look like that. Okay. So we know that there is an inverse function. So here's what we know. We know that whatever the inverse function is, the natural log of it will undo the inverse function and give you x back. We also know that if I take the natural log of e to the x, we can bring the exponent down front by property of logs. And then the definition of e is that the natural log of e is 1. Okay. So this is something else. The natural log of this thing will also give us x. And so I've got the natural log of the inverse function is the natural log of e to the x. And since the natural log is 1-to-1, if you have the same output all the time, you have to have the same input all the time. And so this gives us our formula for the inverse is e to the x. Okay. So once again, when you see this, when you see these functions back in pre-calculus, back in college algebra, they typically introduce the exponential functions first, tell you what e is, and then move that way. In this course, we've kind of gone and done it backwards, but we get to the same place at the end. So here are the properties of the exponential functions. All right. Once again, as inherited from the log function. So we've got the inverse properties. The natural log undoes the exponential, and the exponential undoes the natural log. All right, so if you plug the functions into each other, they undo each other. Just like if you take the cube root cubed, the cube undoes the cube root. The cube root undoes the cube. Okay, so same kind of relationship here. Here's the graph. From the graph, we get that the domain is all real numbers. So the domain is everything. The range is positive. And I can't tell you how many times this property comes into play. E to the anything is always a positive number. Okay? So e to the anything is always a positive number. It's never 0, it's never negative. Okay? So that's going to be something that you'll be able to use when you go on the final, when you're looking at your graphs. You'll be able to use this property quite a bit. As far as limits are concerned, the limit as x goes to infinity of e to the x is infinity. And the limit as x goes to minus infinity of e to the x is 0. So some people like that, e to the minus infinity, or e to the infinity is going to infinity. E to the minus infinity, that's going to 0. And once again, those will be helpful on your final when you're looking at that graph. That'll help you out. And then you've got the product rule, quotient rule, and power rule. These are the laws of exponents you've known for ages now, but you can actually inherit these from the natural log by essentially turning the log inside out. So for example, with the natural log of the product, you can prove using derivative properties, is the sum of the natural logs. And so this means that if you look at the natural log of e to the little m times e to the little n, that would be the natural log of e to the little m plus natural log of e to the little n, which would be m plus n, which, using the inverse property, is the natural log of e to the little m plus little n. And then using the one-to-one property of natural log, you get it that way. So once again, you can get everything that we know about exponential functions. Instead of starting with them, looking at their properties, and then deriving log properties, you can go backwards because they're inverses. And if nothing else, that's kind of the big idea. When you have an inverse function, if you know about the function, you really know everything about the inverse. You follow? Let's look at the derivative rule. Let's say try to figure out the derivative of e to the x. So what we can do, say, okay, well, I'm trying to figure out a derivative rule. I've got this x in the exponent, so I can use logarithmic differentiation. So if I don't know how to work with exponents, I can take the log here. And once again, I can use log properties. Once again, that's 1. So once again, I can use properties of logarithms to tell me about the exponential. Because now I can take the derivative of both sides with respect to x. Oops, that's 1. And to your surprise and delight, you see that the derivative is itself. So the derivative of e to the x is e to the x. And so here's our new derivative property. The derivative of e to the x is e to the x. You can chain rule it up. If you're taking the derivative of e to the something, it's going to be e to the something times the what? Derivative of that something. What rule is this again? That's your chain rule. Okay. But what this means graphically, if we think about what this means graphically, it means that the slope at any point is the same as its y value. So the farther up you go, the steeper it gets. And we'll talk about that in a little more detail here in a minute. But for example, at the point 0, 1, the y value is 1. That's the same as the slope. Okay? At the point 1, e, now the slope is e. You follow? So the higher up you get, the steeper you get. Okay? And then as you go the other way, right? The smaller the y value, the shallower the slope. Okay? Until eventually it levels off to nothing. So that's once again, that's the geometric interpretation of what's happening here, but there's something else happening in terms of rates of change. So just like with the natural logs on Thursday, the derivative rules apply to e to the x just like they do any other function. So if you want to take the derivative of x e to the x minus e to the x, you look at this and you analyze it the same way we looked at the basic derivatives from chapter 3. So you've got your sum and difference rule, you've got your product rule, you've got your quotient rule, you've got your power rules. The new rule we're learning today is the exponential rule. The derivative of e to the x is e to the x. More generally, the derivative of e to the something is e to the something times its derivative. All right, so what property would we hit here first? Sum and difference. So this would be the derivative of x e to the x minus the derivative of e to the x. What's the derivative of x e to the x? What rule do I have to use there? Product rule. Even though it's not, you can read it as x e to the x, it's really x times e to the x. Times means multiplication. Product rule. Derivative of the first factor times the second plus the first factor times derivative of the second. And the derivative of e to the x is e to the x. That's the new rule. You follow? It looks like nothing happened to it, but it's its own derivative. What's the derivative of x with respect to x? 1. Derivative of e to the x with respect to x? E to the x. So I have x e to the x plus e to the x minus e to the x. So what happens here? They just cancel out, and I'm left with x e to the x. Make sense or not, folks? And once again, don't forget, we can check these graphically on Desmos. So just to remind you how you do that, you type in your function, type in the f prime of x, click off the function, and then you write your answer. And the graphs are indistinguishable. You follow? So don't forget, you have Desmos you can use to check your answers. All right, number 2, a of t equals 50 e to the minus t. Find a prime of t. So a prime of t means we're taking the derivative. The independent variable here is indicated to be t. So we're taking the derivative with respect to t of 50 e to the minus t. What rule can we first use here? Bless you. Constant multiple. I got a 50 times e to the minus t. That's a constant multiplying the function, so I can factor that out. And now I use the new rule. Bless you. I'm taking the derivative of e to the something. The derivative of e to the something is e to that thing times the derivative of that thing. So 50 e to the minus t. And what's the derivative of minus t with respect to t? Negative 1. So I get negative 50 e to the minus t. You see what's happening or not, folks? Let's take a look at this function. Y equals e to the 2x sine of 3x. So this combination is actually a pretty common combination. If we kind of take a look at what's happening here graphically. We've got the think of this as a sine wave here. When you have like a sine wave in trigonometry, the A represents the what? That's the amplitude. All right. So here we can think of this. We've got your sine of 3x. But its amplitude now is e to the 2x. So let's take. It doesn't look like this is helping because it just takes off so fast. So you've got your sine wave here, but the amplitude is e to the 2x. So you're taking this sine wave and you're multiplying it by this exponential curve. And we'll see if we can kind of see what's happening there. Is that the exponential curve is just blowing up the amplitude of that. Okay. So they ask us to find dy dx. Dy dx, remember, is just another way for them to ask for the derivative with respect to x. Right. What rule do we have to use there? You've got e to the 2x sine of 3x. How are the e to the 2x and sine 3x connected? They are multiplied, so therefore we have to use the product rule. All right, derivative of the first factor times the second plus the first factor times the derivative of the second. And what's the derivative of e to the something? E to that thing times the derivative of that thing. And then we still have the sine of 3x we're multiplying by there. Plus e to the 2x. What's the derivative of sine of something? Cosine of that thing times its derivative. And what's the derivative of 2x with respect to x? 2. And we'll migrate that constant multiple out front. And what's the derivative of 3x with respect to x? 3. So we'll migrate that out front. And there it is. Okay. Any questions, folks? In a way, we left the nicest formula for the end, right? It's basically itself. You just have to adjust by chain rule if needs be. Find the equation of the tangent line. All right, tangent line. Y equals slope of the tangent line times x minus x naught plus y naught. If you have y as a function of x, and you're looking at x equals a, the slope of the tangent line is the derivative at a. The x naught is a. And the y naught is f of a. So these go way back to the beginning of chapter 3, right? That was section 3132. Seems like forever ago, but it was really like what, 5-6 weeks ago? So we're looking at f of x being e to the x. So what's the derivative of e to the x? E to the x. So the y value at 0 is the same as its what? Same as its slope. You follow? So you put these together, y equals f prime of 0, x minus 0 plus f of 0. 1 times x minus 0 plus 1, and y equals x plus 1. Okay. And once again, you can check tangent lines by doing what? Graph the function, graph the line near that point. The graph of the function and the graph of the tangent line should be what? Indistinguishable. So fire up. And we'll take a look here. I'll go say minus 1 to 1 for the x, 0 to 2 for the y. There it is. You can see the local linearity. Okay. All right, any questions on taking derivatives of exponential functions? All right, and we got example 11 here. Here's some more for you to practice. The answers are here. If you don't get the answers, or if you have questions on the methodology, you can always fire up that video. Example 12 is kind of like something we had for sine and cosine. You know, when we first talked about derivatives of sine and cosine, we observed that this frequency in here, this coefficient of x in here, is just saying that this sine wave goes twice as fast as the other one does. So when you go to find the slope, in the same way, once you start taking more and more derivatives of exponentials, you'll just notice that this exponential is going twice as fast as the original exponential. So that too is just going to come down front. Okay? So in general, the derivative of e to the kx is just going to be k e to the kx. Right? And where this really saves us time is when we go to the integration property. But let's take a look at example 13. So example 13 really talks about why exponential functions are so useful to us in terms of rates of change. So this is the classic problem, the number of yeast organisms in suspension, n of t minutes after being introduced, is given by this formula. Find and interpret n of 0 and n prime of 0. So here they give us n of t, n for number of organisms after at time t. So let's look at n of 0. Once again, n of 0 means everywhere we see a t, we're going to sub in a 0. So we're going to get 5,000 e to the 0.0077 times 0. And what's 0.0077 times 0? 0. And once again, what's e to the 0? 1. Okay. So that's the find part. That's the calculate. What's the interpret part? What does this mean in terms of the number of yeast organisms in the suspension? So t equals 0. That means when? At the start or initially, there are how many yeast organisms in the suspension? 5,000. You follow? Now let's calculate the derivative. So taking the derivative with respect to time, because that's the independent variable indicated there, 5,000 e to the 0.0077 t. So that 5,000 is a constant multiple, so what can I do with it? factor it out. Now I'm just focused in on the derivative of e to the 0.0077t. So this is the new rule we learned today. What's the derivative of e to the something? E to that thing times its what? And so what's the derivative of 0.0077t? 0.0077. I'm just going to keep this multiplied out because of what's coming later. And so that's our derivative. And if I plug 0 into that, and as before, what's e to the 0? 1. Let's see what decimal that works out to be. 38.5. So that's the find part. We found it. Okay? But now we need to interpret that in terms of yeast and time. So remember, derivatives are what? They're slopes, they're rates of change. Okay? So the numerator is going to be the outputs. The denominator are going to be the inputs. What are the outputs of this function? The outputs are the what? Number of yeast. And the input is the time measured in what? Minutes. So that's minute. It's the number of yeast per minute. So once again, we've put in t equals 0. So initially, what's happening with the number of yeast? Is it increasing or decreasing? Increasing because the derivative is positive. At a rate of what? 38.5 yeast per minute. Make sense or not, folks? And one of the problems on your take-home involves here's a derivative function involving the rate of change of the growth of something. It's once again the same concepts we had in chapter 3. We just have a different function that we're using to model these phenomena. Now, number 2 really gets at what characterizes these exponential functions and why they're so useful out in the wild. So in number 2, it asks us to find and interpret n prime of t over n of t. Because when we found n prime of t, it looked pretty much the same as n of t. The only thing that was different is we picked up this multiple. So if we just plug in our formulas here, we had a 5,000, 0.0077, e to the 0.0077t. The original function was the same thing. It had the 5,000. It just didn't have this other multiple that came down from the exponent. You follow? So look at what happens. Regardless of what t is, this ratio is always the same. You follow? And so what we call this, we call m prime of t a rate of change of n with respect to t. When you divide by n of t, this is called a relative rate of change. Because you're looking at the rate of change divided by the function itself. That's a relative rate of change. And this is a constant. In fact, if I think of this as a percentage, it's saying that the relative rate of change for this situation is a constant 0.77%. You follow? So when you hear about things increasing at a 2% rate, or depreciation happening at a 5% rate, those constant percentage changes are always going to be modeled by exponential functions, because those are the functions that have a constant percentage rate of change. So constant rate of change is where your derivative is just a constant. This corresponds to linear functions. If your derivative is a constant, then you get linear functions, assuming, of course, the rate isn't zero. A constant relative rate of change, f prime of x over f of x, is a constant. That's going to give you one of these exponential functions. Okay? And if you're interested more in this, then I encourage you to watch the video that I've got on growth models. The video on growth models, once again, you should watch it at some point. But it also then goes in and talks about how scientists phrase their laws in terms of these rates, and then how exponentials come out of it. So for example, in chemistry, you have your first order chemical reactions. The rate of change of concentration with respect to time is equal to some, right? That's your first order chemical reaction. You can rearrange this. And sure enough, there's that relative rate of change being a constant. Okay, so that's where all that stuff comes from. All right, exponential functions with bases other than e. So now we're literally coming full circle. Like normally in college algebra, you start with exponential functions looking at the function 2 to the x, something that doubles all the time. How would we figure out a derivative for that? Well, we could do one of two things. We could do logarithmic differentiation, or we could use the change of base property. So if you look at 2 to the x, you can use the inverse property. This is e to the natural log of 2. Because e and the natural log undo each other. And then you could multiply here e to the x natural log of 2. So one way to get the derivative is to just change the base. And the derivative of e to a x times a constant is just going to be e to the x times that constant. The derivative of the exponent will just spit the constant out. And then you can redo your properties there to get back to 2 to the x. Make sense or not, folks? Okay. So in the same way you could just change your base all the time with logs, you can change your base on exponents the same way. Alternatively, you could find the derivative using logarithmic differentiation. If you've got y equal 2 to the x, you can take the natural log of both sides, use properties, implicitly differentiate. And you could get the derivative property that way. Okay. Either way, the long and short of it is, if you're taking the derivative of something and the base isn't e, then you have to multiply by the natural log of 2, which of course is the opposite of what happens if you try to take the derivative of the log of something other than e. That's what we talked about on Thursday. So Thursday we learned that the derivative of log base 2 of x was the natural log of x divided by the natural log of 2. Excuse me. Derivative of that, which was 1 over x natural log of 2. So we had to divide by the natural log of 2. And so today we're learning the derivative of 2 to the x is 2 to the x times the natural log of 2, right? So in the one case, we're dividing by natural log of 2 to account for the different base, and here we're multiplying by natural log of 2. And once again, there's a couple different ways you can go through and derive the formula. And then it's up to you what you want to do with it. If you want to memorize the formula, fine. You can memorize the derivative of b to the x is b to the x natural log of b. And notice when b equals e, the natural log of e is 1. The derivative then of b to the something is b to that thing times the natural log of b times the derivative of that something. Well, here once again, b is a constant. So these are the usual caveats when it comes to talking about exponential functions. Okay? So it's up to you how you want to do it. You could just remember the e formula and then change the base, or you could remember this new formula. It's up to you. Once again, the more you understand, the less you have to memorize. Okay? And then there's a couple of videos, a couple examples to do. Finding a derivative here. This is, I like this function because here the x and the 3 are switching places. You've got a power function times an exponential function. And this is a lot like the yeast example, except it's a compound interest problem. So yeah, it's good for you to go through and do those. All right. So as we mentioned on Thursday, anytime you learn a new derivative formula, you're going to get these formulas showing up then in integrals. So let's do some integration here. One of the handouts you got on Thursday, and if you weren't here Thursday, you can pick them up today. They're still there today. Was this handout? So this has the basic integration formulas. It's got your exponential and log on there now. And then you've got the inverse trig stuff. And you got your basic strategies. So this is what we've kind of developed here, this course. So, you try to do the algebra stuff first to break things up as best you can. If the algebra, then if you're still stuck, then you always try one of these substitutions. Let u be what's in parentheses, and so on. So for example, we're trying to integrate cosine of e to the 3x times e to the 3x dx. And the thing about these exponentials is they're kind of slippery because they're pretty much their own derivative. You follow? So if we were to follow the rules of thumb, we'd look at this. You've got a cosine of e to the 3x times an e to the 3x. There's no addition, subtraction that we can take advantage of, so we'd be stuck with the substitution. Our very first rule of thumb from, it was literally what, a week ago? Or no? Was it just a week ago? I think it was. Yeah, just a week ago. We're going to let u be what's in parentheses. And so then we calculate the du. And what do we get? What's the derivative of e to the 3x? 3e to the 3x dx. Do I have a 3e to the 3x dx? No, but I could fix it up to get one by multiplying and dividing by 3. So either you look at this and say, okay, well, I do have this. I could make that a 1/3 du. Or go in here and multiply and divide by a third. At the end of the day, you're going to get 1/3 integral. This is what we were letting the u be, because that was a thing in parentheses. And then that would be your du. Right. So no matter which method you used, you should get a 1/3 out front, and then integrating cosine u du. Any questions on the substitution there? See where the third's coming from? All right, now we can integrate this. This is 1/3 integral of cosine of u, sine of u plus c. And since this is an indefinite integral, you've solved it for you. Now you got to solve it for me. Got to put the x's back in. And there it is. Oops, plus c. And what's the ultimate check of these antiderivative questions? You start with your answer and do what? Take the derivative. If you did a u substitution to help you find the integral, then when you go to check your answer, you're going to end up using the what? Chain rule. So I'll leave that to you. All right, number 2. We're asked to integrate the square root of natural log of x plus 9 over x dx. Once again, this looks like nothing that we have on the basic integration formula sheet. I mean, there's a log in there for one. We've got nothing that tells us how to integrate logs. We do have a square root. We do have some special formulas that involve the square root, but in those special formulas, the square roots are where? In the denominator. All right, this square root is in the numerator. So let's go ahead and do what we usually do. We'll rewrite that square root as a what? One-half power. And then we'll try for a substitution. Our first rule of thumb, let u be what's in parentheses. If I do that, I'd calculate my du, and what would it be? We have to go back to Thursday. What's the derivative of the natural log of x? 1 over x. The derivative of 9 is 0. Do I have a 1 over x dx up here? We do. I could rewrite it. Natural log of x plus 9 to the 1/2 times 1 over x dx. Sure enough, there it is. Okay. So this very complicated looking integral that's got square roots, logs, and division in the land of u reduces down to what? Instead of natural log of 9, natural log of x plus 9 to the 1/2, it's just what? U to the 1/2. And 1 over x dx, that's just what? Du. So here we go. We're back to a power rule. So how do we integrate u to the 1/2 du? The exponent gets promoted. We add 1 to it, and that's going to give us an exponent of what? 3 over 2. We divide by that new exponent. That means we flip it over to get what? 2/3. This is an indefinite integral, which means we need to get it back to the original variable. U is holding the place for what? Natural log of x plus 9, so 2/3 natural log of x plus 9 to the 3/2 plus c. And once again, what's your ultimate check here, folks? Start with your answer and take the derivative. Since you used a u substitution to help you find the integral, when you take the derivative to check your answer, you should use the what? The chain rule. Okay. All right, so here's a few more for you to work on. The answers are there. Once again, try to work them through. If you can't get the answers to match or you're not sure how to get started, you can fire up the video and do that. Number 4, there's a hint there on there. You can kind of see by adding these extra functions in there with these logs and exponentials, it's weird. The logarithms, you take the derivative of a logarithm, it goes from a logarithm function into like an algebraic function. You follow? It goes from a natural log to like a 1 over x. Whereas the exponential function, you take the derivative of that, it pretty much stays the same. So when you put these in to the integrals, sometimes it's not very obvious what you're going to let your u be. You have to play around. So you make a choice for u, calculate the du, see if it gets you anywhere. You follow? Sometimes you just got to start over and try something else. So you just got to keep up with it. Which, that's part of the reason why the last assignment here, that there's no timed test part to it, because you don't have the time to be playing around with this. So once again, before you move into Calc 2, whenever that is, the week before, break out that integration review sheet and start working on those, okay? Because you want to make sure your integration before Calc 2 is in top form. The other way exponentials and logs can show up in integrals is by reversing the derivative formulas that we have for them. And so if you look at where the u is in these formulas, that gives us a couple more rules of thumb. Let u be what's in the exponent, or let u be what's in the denominator. Does that make sense or not? So these are two to three new formulas here. So we take a look at example 18. We're asked to integrate 3 to the tangent of x times the secant squared of x dx. And you may already recognize secant squared there as being the derivative of what? Tangent. So once again, as someone mentioned back when we were doing substitution, sometimes you can see the du sitting there. You follow? And you can work backwards to figure out what the u would be. So we'll try let u be what's in the exponent. And then we'll calculate the du. And so this potentially problematic integral in x turns into what? In the land of u, 3 to the tangent is going to be 3 to the u. And the secant squared x dx is going to be the du. Does this make sense or not, folks? And we know when we take derivatives of exponentials other than e, you get that exponential back, but you have to multiply by the natural log of the base. So when you integrate you're going to get that exponential back. But instead of multiplying by the natural log of the base, you have to do what? Divide by the natural log of the base. And finally, since this is an indefinite integral, it's an antiderivative, we need to get everything back in terms of the original variable here, which is x. You can check your answer by taking the derivative. You can check your answer graphically on Desmos, however you want to do it. Any questions on this one? So what's nice about integration formula problems is it gives you a chance to practice the derivative formulas right along with it. Let's take a look at number 2. Asked to integrate tangent theta d theta. So if you think about the integration formulas we have for involving trig functions, tangent is left out. We've got an integral for sine and cosine. We have integrals of that feature tangent, you follow? But we don't have an integral of tangent itself. And the reason we don't have it is because we didn't have the integration formula till now. Because what do you typically do in trigonometry when you're stuck with something involving a tangent? You rewrite it in terms of sine over cosine. Yep. So this is sine of theta over cosine of theta, d theta. And we're going to need a u substitution. One of the new rules of thumb we have is to let u be what's in the denominator. Do you see why this is going to help us here? Because if I let u be the cosine of theta, what's the du? It's negative sine of theta, d theta. Remember that negative is really a what? That's really a multiple of negative 1. So we can handle that negative in the same way we handle all the constants. So in the land of u, we'll just have this negative out front. Sine of theta d theta, that's our du. And I'm left with 1 over u. Any questions on the substitution or then what it looks like? And now this is one of our new formulas. And we talked about this on Thursday. In order to capture all values of u plus and minus, we need absolute values. And so there it is, the integral of tangent. Now, if you check out the other summary sheet you got on Thursday, which I thought I had pulled up, but apparently I don't. If you look on this sheet, under integration formulas, there it is. Now notice though, it's got two different options. It's got negative natural log cosine, which is what we have, but it also has natural log absolute value of secant. So let's see how this works, so you're not totally thrown off by this. Remember that negative, once again, that negative is really a multiple of what? Negative 1. Now let's use properties of logs. We can bring that exponent up. And remember, what does the negative 1 exponent means? It means what? 1 over. So far so good, folks? Now, how do absolute values work? I could rewrite this as the absolute natural log of the absolute value of 1 over cosine, because the absolute value is there to make sure that the cosine is positive. So I could flip the cosine over and then make sure it's positive. And what's 1 over cosine, folks? Secant. So with these antiderivative formulas for tangent, cotangent, secant, and cosecant, all of these are equivalent using log properties and then trigonometric properties, trig identities. Okay. It just, it depends. You can add these to your index cards. You can have both of them down. Sometimes one may be more convenient than the other. I don't know. Then number 3, integrating 1 over x times the natural log of x dx. We know you got to let u be something. So once again, you may recognize that you've got a 1 over x here. And 1 over x is the derivative of natural log. Or you just try things. You let u be the denominator, let u be other things. But if you finally let u be natural log x, the du then would be 1 over x dx, which you recognize is there. And so in the land of u, this turns into a 1 over u du. And this is one of the new integration formulas. This is the natural log of the absolute value of u plus c. So natural log absolute value of natural log plus c. And once again, the ultimate check to all of these integration formulas is to take your answer and take the derivative. Either look at it graphically on Desmos, but ideally you'd go through the analysis. Example 19, more practice using these integration formulas. Let's look at example 20. Example 20 reintroduces another algebraic manipulation we can do to help us figure out these integrals. Now, if we just had a 2x down there, we could break up the numerator, 3x over 2x minus 2 over 2x, and we'd be good to go. You follow? The problem is we've got this plus 1 down there, which doesn't make things easy for us. So, if we think back to college algebra, or actually beginning algebra, we know that if we look at what we've got going on here, we've got a polynomial p of x divided by a polynomial q of x. And the degree of p is bigger than or equal to the degree of q. Degree meaning the highest power of x. So if I look in the numerator, I've got an x to the first power. That's the highest power upstairs. The highest power downstairs is also what? X to the first. And when that happens, that means that you can do long division. So just like when you would have an improper fraction, if you had like 10 over 7, the 10 is bigger than or equal to the 7. That means we could rewrite this as a mixed number. You take 7 into 10, it goes one time. You multiply and subtract with the remainder of 3. That means 10 over 7 is 1 plus 3 over 7. You follow? So that same arithmetic, that same division algorithm, carries over into polynomials. You can essentially take this and think of this as an quote-unquote improper rational function. You can do long division to rewrite it in the same way we wrote this. Okay? So let's see if we can do that. So this problem is really 2x plus 1 divided into 3x minus 2. And so we're taking 2x into 3x. So I think over here, do some scratch work. 3x over 2x. That's going to go 3 halves times. So I'm going to put the 3 halves here. Since that's a constant, I'll put it over this constant. And now I'll do the same thing we did here. I'll multiply, and then I'll subtract. So I'll multiply this by both terms. I got to multiply 2x plus 1 times 3 halves. Now the 3 halves times the 2x has been designed to cancel the 2's out and leave the 3. So whatever you multiply here, this will always work out to be the same because we're designing it to cancel out. But then don't forget to multiply it by the second term here, in this case 3 halves. And then what did we do? Whoops. Oh, now I lost it. Is we subtracted. Okay? So we're going to subtract the whole thing here. Just like we did before. The 3x's are designed to cancel out. So if the first terms aren't canceling out, that means you need to redo your initial calculation there. I've got a minus 2 minus 3 halves. So if I wanted to keep everything with halves, that'd be minus 7 halves. And notice now there's no x in there anymore, right? There's no... so this is my remainder. This is my quotient. This is my divisor. So here's what this algebra does. It does the same thing this arithmetic does. So when you do this arithmetic, 7 went in one time with the remainder of 3. The 1 was the quotient, plus the remainder over the divisor. You with me or not, folks? So that's what I'm going to do here. So the 3x minus 2 over 2x plus 1 equals the quotient plus the remainder over the divisor. Now, what's the advantage of this? We've taken something that we couldn't integrate right away, or we probably could have, if we could have done some u substitutions and some shenanigans, but the long division works better and it works more general, to now integrating this. You follow or not, folks? And so you can go through the usual sorts of machinations. You'll get 3 halves x from here, minus 7 fourths, natural log absolute value, 2x plus 1 plus c. Okay. So usually long division is something you may have forgotten about. We've got some review materials for you. If you need extra practice on this, let me know. Normally you just have to do it a couple times to remember how it works. It literally is the same exact algorithm that we're doing here. Okay. Any questions on the division or then the integration? Does this look familiar to you? And then there's another one you can practice on. All right, let's take a look at example 22 here. This is very similar to one that's on your final, but it talks about the rate of change in value of a car in dollars per year, T years after its purchase. So notice what they're giving us here is they're not giving us V of T. They're giving us what? The derivative. You follow? So this is telling us the rate of change. So for example, they don't ask for it, but if I look at V prime of 0, what's that equal to here? Negative 2,000. So that means initially you're losing $2,000 per year on this car. That's depreciation. You follow? All right, so find and interpret the integral from 0 to 5 of V prime of t dt. So that negative 2,000 is just a what? Constant. So what can I do with it? Move it out front. Now I'm looking at integrating negative 0.2t from 0 to 5. And this is where the comment earlier about taking derivatives of exponentials comes into play. So we know that when we take the derivative of e to the kx, we're just going to have a multiple k pop out, right? So that means if I want to integrate in e to the kx, I could go through a u substitution, you follow? Or I could just take advantage of what I know is going to happen. I know that the integral here is going to be more or less e to the kx. But when I take the derivative, I'll be multiplying by a constant k. So when I integrate, to take that into account, I'm going to do what? Divide by that constant. Make sense? So this is, once again, it's like when we were integrating cosine of kx dx. Right? It's just one of those little time-saving tips. It comes from the chain rule, and it's up to you. If you want to go through a formal u substitution here, that's fine. But the point is we can avoid it. Because the antiderivative of e to the minus 0.2t is going to be more or less e to the minus 0.2t. When I take the derivative, the constant minus 0.2 is going to pop out, so I'm going to divide by that constant when I integrate. You see how we're using this property? And since this is a definite integral, I'm evaluating this from t equals 0 to t equals 5. I've got a negative over a negative, which is a positive. The 2's will cancel, and then I'm taking 1,000 divided by 1/10. So that would be 10,000. E to the. Plug in the 5. Minus 10,000. E to the, plug in the 0. And then go through, what's that calculate out to be? Negative 6,321.21. So that's the value of that integral, is minus 6,321.21. But now we're asked to interpret what that means in terms of the value of the car. So this is where we go back to last week and we remember the net change theorem. So if you remember, the integral from 0 to 5 v prime of t dt, using the fundamental theorem of calculus, would be the difference v at 5 minus v at 0. So once again, this is that net change in the value over the interval from 0 to 5. So if this integral is negative 6,321.21, then what does that mean in terms of the value of the car? Over the course of the first 5 what? Years, the car has lost value of, that much money. Make sense or not, folks? The value 5 years from now minus the initial value is negative. That means we've lost value. The car has depreciated. Make sense or not? So once again, this is the same concept we had last week, the net change. We're now just using the exponential functions because that's the function that models this kind of behavior. If the initial value of the car was $10,000, find a formula for the value of the car, v of t. And so this is exactly the kind of thing we did last week. So this is from the section 6.1 stuff. You've got your initial value of the car. So that's your initial value times your net change. Notice you get the same antiderivative we had before, except now we're plugging the t in. So instead of having the 5 in there, we have t in there. And so then we get down to that formula. Okay? So essentially the same computation we did before, except we're leaving t in instead of plugging in 5. And then you have a chance to work through something similar here on this video. And once again, this is very similar to one that's on your final. Okay? So I think this is the last one here we want to do today. And then this is all the material that's on your final. So like I mentioned last week, tomorrow we'll talk about the loose ends. We won't do a lot of detail. We'll kind of give an overview of the hyperbolic functions. Talk about some numerical integration, but we won't do much tomorrow. I wanted to make sure you at least had all the bits and pieces for the final, so you can start working on that as soon as possible. But the thing about these exponentials, like I said, they can be kind of slippery, and that's why there's some of these are on your final as a bonus. I think your final has 4 or 5 exponential function integrals on there, and they all look really the same, but there's subtleties that with practice, you'll figure out. And hopefully by making them a bonus, it'll encourage you to actually try them. But, let's say you encounter this integral, and you try all the basic things. You could let u be e to the x, the du would be e to the x, and there's no e to the x. You could rewrite it, let u be e to the 2x minus 1, and once again, the derivative of that would have e to the 2x in there, which you don't have. You follow? So a lot of times when you're making substitutions with e to the x's, the problem is if you're trying to do that and there's no other e to the x's, you can get stuck. You follow? So there's a couple ways to handle it. The hint says to multiply by e to the x divided by e to the x. Now, ostensibly, the e to the x dx, ostensibly that's like what they want the du to be. So if they want the du to be e to the x dx, then that means that the u itself would be e to the x. Does that stand to reason? So that means that this e to the x, they're thinking of as u. And what can I do with that e to the 2x then? So what's the relationship between e to the 2x and e to the x? Yeah, this is e to the x what? Squared. So look at what happens now. In the land of u, this becomes a 1 over u square root u squared minus 1 du, which is one of those new formulas we learned last week. All right? So last Tuesday, I think, we learned that this one was the inverse secant. Since e to the whatever is always positive, I don't really need absolute values. But you can kind of see how slippery these integrals can be with exponentials. So if you do a u substitution and you don't have what you need, you could either solve for x in terms of logs and do it that way, but most students freak out when you do that. So just multiply in what you need and then make sure you divide it out. And since it's a variable, you can't take it out front, but normally that'll help solidify what else is going on in the integral. And then here's another example of this kind of thing. So here's how the homework breaks down for 7.2 and 7.3. Once again, there's algebra review parts. The way your book breaks up this material is they have e to the x and natural log of x in 7.2, and then they have the different bases in 7.3. Okay. I would have organized things differently, but whatever.